We want to solve a static harmonic forced motion of infinite string. Okay, so this is an infinite string with a tension force T and the density rho, and under some loading Qxt. Okay, the governing equation is y xx minus c0 square y tt equal to minus t q xt. Okay, that's a loading function, and the c0 is the square root of t over rho, so the wave speed propagating in the string. All right. Now, if qxt minus 1 over qxt, we say this term is harmonic, the real function of px, okay, and e minus I omega t. Okay, this is my harmonic loading function, right? Then, due to the loading functions harmonic, so we can assume our solution as y xt equal to real part of the yx, okay, and the exponential minus I omega t. Okay, so this to be determined the yx. So we insert this equation to equation 1, okay, and we'll get yxx plus omega square c0 square y equal to px. Okay, so this is a ODE differential equation. Okay, then we apply the Fourier transform on this equation 4. Okay, then we get minus gamma square y bar, okay, y bar plus omega square over c0 square y bar and p bar. So this is equation 5. So after Fourier transform, we got the algebra equation. So here we can solve the y bar as minus p bar over gamma square minus omega square c0 square. All right. Yeah. So gamma is a variable. We transform the x to the new variable gamma. Okay, so this is equation 6. Okay, then so we have to do the Fourier's inverse about the y bar. Okay, now we'll do we get a yx. And is equal to minus 1 over square root 2 pi minus infinitive to infinitive p bar gamma e minus gamma x over gamma plus omega over c0 times gamma minus omega over c0 and d gamma. So this is inverse function for the Fourier transform. Yeah. All right. So this is the work we have to do. So once we solve this integral, we got a yx, then we're back to here, we get a solution. Right? We got a solution. So this is our steps to solve the problem. Okay. Okay. So the way we do the integration, we will use the residual theory in the complex plane. So let's let gamma, the variable here, is a complex variable with a c plus I eta. Okay, yeah. Then for the integration, on complex plane. Okay, and the gamma equal to plus or minus omega over C0 are poles. Okay, poles, single point. Yeah. Then, okay, so the contour integration method is used to do the integration of equation number 7. Okay. 7. Okay. All right. Then, so first thing, we have minus I, suppose, sorry, here have I minus.
你那个是 inverse 啊，就是那个傅立叶是反转换嘛。
是啊。
那个 exponential 应该不能有负号才对。
不能有负号。
对啊，有负号的话是正转换才是有负号 ，exponential 加上有负号。
没有，好像是负转换吧。
是啊，我昨天还特意去查，是逆转换是正号，正转换才是负号。你要从昨天就一直有，他讲义上好像写错，然后你一直有抄错。
我抄错吗？
正转换才是有负号。
正转换，我的笔记都没有符号，我不晓得，我没有去 check。但是你们 check Google 看一下。正转换没有符号，负转换才有符号。你查书了吗？你的书有问题吗？没有啊，我的公式都是正转换才有。正转换是正号，负转换还是负号？
对，是吧？
不然我们那个公式会出现问题啊。我们那个 Fourier transform 是OK。Fourier transform 我们对这个 y(x) 的这个微分的话是 1/2 派，负无限大无限大的 y(x) 的 I gamma x dx， 好，这是正号。所以你 integration by parts 的话，你会得到 1/2 派 e I gamma x y 减掉。OK， 这都没有，所以就变成这个有 I omega 是就是负 I gamma 负无限大到无限大的 y e I gamma x dx， 所以是负 I gamma 的 y 八。
没有，它那个 exponential 应该要有负号，因为你如果 exponential 有负号的话，它无限大分母就是会那个值会趋近零嘛。然后它那个负无限大是因为，
不是，
是吗？
你这都有正负无限大的问题啊。那这个地方重点是在正负无限大这个值是为零，所以这个才丢得掉。你不要跟我吵，你去看，你 Google 找到了吗？
我刚看了，
是负的。
感觉那个是没错吧？那种这个公数
是正还负？查一个数有那么难吗？
我看是正啊，是负的。老师你看一下，维基百科上面，我印象中之前学也是负吗？为什么逆转换才是变成是负的？那我这个有看错吗？你这样子的话，你这个提出来嘛，你这个负号 I gamma 提出来啊，才是负的。这边有个负号啊 ，integration by parts 啊，才有这个负这个。你下次二次的话就是负 I omega 的平方啊。 这我回去推推看。啊？我等下回去推推看。
还要推不就清清楚在这边还推什么？维基百科是写负啦。负的话就微分就会变成正的嘞。
他是写的。
他写负。
另外一个是求负，也是负的。
也是负的。哦。是吗？记错了吗？笔记都错了。可是我这样正不是 n 次微分的话就所以我们会有个公式嘛 f n 阶微分的 Fourier transform 是负 I omega n 次方的 f hat omega 是吧？一次就是这个嘛，再一次的话就会在 integration by parts 又负的平方了嘛，对不对？要再乘一次负的，是吧？因为这个东西在无限大的，它是 sin cosine 没有什么无限大，它是 bounded。在无限大的值，就是 cosine 里面无限大，那这个没有什么无限大的问题。无限大消掉是这个地方，这个值在两端是为 terminate， 我上次讲过的。好，好吧，我们就先 follow 笔记好了，好吧？如果有错的话，你全盘你反正我们再改吧。所以我的 inverse 才有负的哈。OK， 好。 然后现在这个地方有一个 So here we have a minus I omega x this term. So here okay, right here. Yeah. So my goal is to do the integration minus 1 over square root 2 pi. Then right here is minus infinitive p bar. P bar gamma E minus I gamma x gamma plus omega over C0 times gamma minus omega over C0 d gamma. All right. Then gamma is cos C plus I eta in complex plane. Okay. And the integral actually is for minus infinity to positive on real axis. So if gamma is a real number. So if I want residual theory, I have to do the integration on this plane. So this is gamma plane. This is C eta. And these two values is two real values. So this is a two singular point. Omega over C0 and minus omega over C0 is 2 points. Okay. So our integration majorly is on this real axis. So our contour method, yeah. So we have to select the contour. If I select the contour, yeah. So let's see. This is a fx. No, this is a yx. Okay. So for any given x, I should do the integration. So we have two cases. X for x. If now we say x is larger than 0. Okay. Then the integrate this term minus gamma I gamma x is equal to I cos C plus I eta x minus, and that will be eta minus I cos C x. Yeah. So exponential minus I gamma x equal to exponential eta minus I cos C x. Okay. So for if we choose a contour with lower half circle, because a direction like this. So either I have a contour like this, or this one, and this here, and this is the radius of this contour. Okay, and here we have a small radius we call epsilon. Okay, this is our contour. So if R approach infinity, that means the eta value is approaching infinity. Okay, infinity. So in this term, this will be E eta x times exponential minus I cx. So this is bounded, right? Right, bounded. And for x larger than 0, and eta is lower circle, eta will be smaller than 0, half, lower half. Because all the eta here are negative value. So this term will approach to 0 as eta approach infinity. Minus infinity. Okay. Negative value. Right. So that's why we have chance to cancel the integration along this half circle. To only remain the integration along this line. But still another problem is we have to check we should contain which pole we should, okay? So that's explain why. For x larger than 0, we have to choose the lower half. So for x smaller than 0, we choose upper half circle. Okay? That's what explain why we choose this contour. All right? Okay. So this is the first part for this integration. So first, for this integration on complex plane, this is C, this is eta, and we have two singularity. For x smaller than 0, because the term E eta x exponential minus I cos x, right? Then x small than 0, so eta should be larger than 0. Okay, then we can have this term approach to 0 when or on the radius very big. Okay, for the then this